I come up with trying to get using output voltage power or current power using two extreme cases in the CS type amplifiers. Well, case 1, we can get Vn1 out squared or In1 out squared, which is input shorted. If input shorted, we have no signal input. Input is shorted to ground or AC ground, and something biased and no amplification, just output channel noise is there. Now, so In1 out squared and In1 out of M1 of R squared appears there. Using lemma, these are non-correlated, and each is represented as 4kT over RD and 4kT gamma GM. M1 has GM transconduction GM. M is so this is add up and multiplied by R squared, giving Vn out squared. Because we can get R out equals RD in parallel RO, which is infinity when lambda equals 0, equals lambda equals considered 0. R out is the output in resistance when input shorted. So we can get this. And when our input is open, we have this current In2 out of M1 squared bar, and outlet open, but we don't have output impedance. We don't know output impedance of this, but this generates here the voltage outscared M1 of In square out M1 times RD, and this generates Vn2 out R bar squared bar equal 4kT RD. Now these are non-correlated and add up to get Vn2 out squared bar equal adding this plus this equal 4kT gamma GM RD. There's no feedback, so this modulation doesn't appear. There's no coupling feedback, and so input noise is don't have to be cared. If we don't consider 1 over f neglected. sorry. And we can find out these two expressions are same. So extremely two extreme cases, input open cases. We can use voltage noise power to add up to get output voltage. In input short cases, we can use current power noise. IN output for R add up because of non-correlated cases, and we can get output resistance and multiplies. After multiplying, we can get Vn1 outscared, and Vn1 outscared is equal to Vn2 outscared bar must be, and it's obviously the same in this case. So we use both cases. We can use both cases. We can select. We can choose both. Each cases. We can more useful. We apply one of these cases, which is more useful for the cases in concern. Cases in concern. In this case, this is easier because these representations are easily directly derived, simple format, and output resistance is simple. These formula need to some consideration. This transfer to voltage power, this has voltage noise. But each parameter are simple. Not so. There's not so much different in difficulty in deriving output voltage noise. Well, there's direct derivation. This is non-direct, not directly derived. This expression. This is just a little bit difficult. Needs one step more calculation in brain. Adding just one thought needs just one thought. So this is just a little bit more easier in the CS circuit type in cases. Are there any questions? But I don't accept any question here. I could communicate here. Just recording. Sorry. Not so clearly explained with four-step procedure or two extreme cases to derive output noise or output current noise, circuit noise, case by case. use 4-step procedure or 2 extreme cases. Select one which is more easier for you to calculate output noise or input deferred noise or current or voltage. Just an example is, of course, on page 242 to 43, that is example 713, and some parts is assigned to readers to analyze another way. So next, I'll confirm example 713 and that another way. 2 cases. Which is easier, do you think?